100 years ago, when the Spaniards were crossing the South American Andes, they noticed a mysterious sickness associated with high altitude. One of the first men to record this was a Jesuit priest, José da Costa, who accompanied one of the expeditions. As soon as I came to the top of the mountain, he wrote, I was suddenly surprised with so mortal and so strange a pang that I was ready to fall to the ground. Some in the passage demanded confession, thinking verily to die. His companions thought that there was some poisonous principle in the air. Acosta himself, however, realized that it was the result of a shortage. I persuade myself, he wrote, that the element of air in these mountains is so subtle that it is not proportioned with the breathing of man, which requires something more gross and temperate, and that this is the cause that doth much alter the stomach and trouble all the disposition. For obvious reasons, human beings have always recognized the vital importance of breathing. They've seen it as something on a par with eating and drinking, as one of three ways of supplying the body with something that it needs. But breathing is a rather peculiar member of this trio, because whereas in the case of eating and drinking, it's easy to recognize the physical existence of the substances which are involved, that's not quite so obvious in the case of breathing. For instance, when someone decides not to eat, he can easily see and touch what it is that he's depriving himself of. But when someone holds his breath, he may know that he's living on borrowed time as long as he continues to do so, but he can't see or touch what it is that he's abstaining from. In fact, one could very easily get the impression that what was satisfying about breathing was simply the regular muscular act of respiration itself, and that one might think that air was simply another name for emptiness, were it not for that faint, ghostly draft around the lips as one breathes in, and some of the physical effects that one can produce as one breathes out. Since nature was also moved by an invisible agency, which filled sails, moved boats, stirred water, clouds and foliage, it seemed quite reasonable to assume that air and breath were one and the same thing. So in spite of its invisibility, there was good reason for thinking that air was something more than the empty space between solid objects, and that it had a physical existence in its own right. Now, strangely enough, less than 30 years after Acosta first began to suspect that there was something peculiar about the air up here in the high Bolivian Andes, the Italian physicist Torricelli proved that even normal atmosphere had weight. So much weight, in fact, that it was capable of supporting a column of mercury. Now, according to Torricelli, it did this by pressing down on the reservoir of mercury and forcing the mercury up into the closed tube. In fact, Torricelli saw that air, like water, was simply a transparent fluid, and that all living things were immersed in an ocean of it, in exactly the same way as fish are immersed in the waters of this lake. Well, a few years later, the French philosopher and mathematician Pascal decided to test this oceanic hypothesis. Taking with him a fragile apparatus of mercury-filled tubes, he climbed the Puy de Dôme in central France. And he found, just as he expected, that the height of the mercury column got steadily less the higher up the mountain he went. Well, to him, the explanation seemed quite obvious. There was less air to press down on the mercury reservoir. Well, Pascal's finding immediately makes sense of everything that Acosta had noticed. It wasn't that mountain air contained something harmful, but rather that it lacked something essential. The air at these altitudes was so thin that normal breathing simply couldn't keep pace with the demand. In other words, the breathlessness which people felt at high altitudes was the respiratory equivalent of hunger. It was a sign that the body had recognized and was actively trying to overcome a shortage. Well, now, of course, at sea level, there is no shortage of air, but you can produce exactly the same physiological effect simply by stepping up the demand. When someone begins to take strenuous exercise, the normal rate of respiration is no longer enough for his extra need. The sheer effort of breathing as hard as he now has to may become almost as noticeable as it was for Acosta's companions in the high Andes. The feeling may be quite unpleasant, and unless he's trained, an athlete may be brought to a standstill by breathlessness long before his muscles are exhausted. Now, although this feeling is unpleasant, he doesn't regard it as a symptom of illness. Under the circumstances, he expects to feel breathless. He knows that it will subside shortly after he comes to rest. But if you get puffed without doing any of these things, it's often the first sign that something is wrong, either with the heart, the lungs, or the blood. But why should we make these assumptions? Why should we link these three systems with breathlessness? Well, in fact, making assumptions and imposing order on patterns is something which all of us do all of the time about everything. It's the way we make sense of our world. Now, however hard I try, I can't help seeing a picture in these random splashes that I've made. I'll show you the picture I'm seeing, although no doubt you're seeing another one altogether. So, the mind, it seems, is so intolerant of disorder and chaos that even when we happen to know that the pattern was made at random, or at least as near random as I could get in this case, we automatically edit and reshape what we see until it begins to conform to something which we know, recognize, and understand. Well, the scientists of late classical antiquity also improvised a lively association between the heart, the lungs, and the blood. And although this fiction now makes very little sense to us, it had enough meaning to last the best part of 1600 years. Confronted by the warmth of the body and by the rhythmic ventilation of the lungs, they found it quite natural to draw an analogy with a familiar technical process which showed some of the same features. Well, now, according to the Greeks, the heart was a sort of furnace. It contained a life-giving flame which continued to burn from the first moment of conception. Now, there were two functions to this fire. First, it provided the natural warmth which was responsible for maintaining life, for giving generation and movement. But secondly, it refined the crude incoming blood which was arriving in the heart by mixing it with a draft of fresh air. Now, the theory said the process went something like this. The blood was brewed in the liver, and then, after being loaded with combustible materials derived from the food, it entered the heart. And then, as in a smelter's furnace, the inflammable impurities were burnt off by the invisible blaze. Lightened and purified by its encounter, both with the fire and with the air, it issued from the heart in a swift scarlet stream. Well, this scheme rather conveniently explained the action of the lungs as well. After all, an efficient furnace needs a constant blast of fresh air, and since it was known that the lungs were connected to the heart by a series of pipes or tubes, it seemed quite reasonable to assume that the fire in the heart was ventilated by the indrawn breath. So, then of course the smoky waste was blown off in the expired breath. Well, in spite of its anomalies and contradictions, the theory of fire in the heart helped to bring a large number of well-known facts into one consistent, systematic scheme. It helped to explain the natural warmth of the body, and also the constant intake of breath, the ventilation by the lungs, and also the fact that expired breath seemed warm and even seemed to steam or smoke on cold air. What's more, it also accounted for the fact that blood was thick, purple and sticky as it entered the heart, and had turned bright and scarlet as it left it. So presumably it must have undergone some chemical transformation. And since fire was the most powerful agent of material change which was known to the ancient world, after all it was used for smelting metal, the theory of a cardiac furnace just like this must have seemed very reasonable indeed. Well, this theory was given its most systematic expression by the 2nd century Roman physician Galen. For him, the physiology went something like this. Blood from the liver entered the heart where it came in contact with the innate heat. This burnt off all the impurities. The purified blood swept into the arterial system while the smoke was blown out through the lungs. This theory assumed that blood could make its way from the right ventricle into the left through minute holes or channels in the central wall that separated the two chambers. Unfortunately, no such holes existed. But since the muscular wall, or septum, happens to be roughened and pitted, the scientists who followed Galen assumed that these little pits were the entrances to the otherwise invisible channels. Well, when the 16th century anatomist Vesalius actually tried to push a bristle into one of these pits on the surface of the wall, he found it quite impossible to get it through. And yet the weight of the traditional theory was so strong that he managed to persuade himself that the blood had somehow seeped, or as he said, sweated through channels which were too small to be seen by the naked eye. So, in other words, the scientists held to the traditional theory in spite of the absence of the visual evidence. Now, this isn't an example of dishonesty or wishful thinking. It often happens in the history of science that a theory implies the existence of an anatomical structure which simply can't be found at the time. And if the theory is persuasive enough, it may raise expectations to the point where contradictory evidence is either disregarded or else explained away. And sometimes, later on, when optical instruments have improved, the structure is found to have been there all the time, just as the theory said it would be. In this case, however, the theory was wrong. It's much easier these days for a scientist to be right, since he has such a wealth of engines and machines from which to draw fruitful analogies. We find it hard to say what something is unless we can say what it's like. Confronted by some natural process whose workings are mysterious, scientists often try to explain their action by comparing them with something which they clearly understand. And for obvious reasons, we find it easier to understand processes for which we ourselves are responsible. In the ancient world, the furnace was one of the few metaphors available. But as we'll see in a later program, when pumps began to be widely used during the 16th century, scientists were presented with a completely new model for thinking about the action of the heart. Armed with this alternative model, some of the anomalies and contradictions of the ancient one, which had been there all the time, now became apparent to the scientists of the Renaissance. For instance, if the heart really was a furnace, it would need air directly supplied to it from the indrawn breath. But when Leonardo da Vinci actually tried to force air down the windpipe and into the heart, he found it quite impossible to get it beyond the lungs, which meant that the air couldn't have mixed with the blood in the heart. It had to have done it in the lungs. Now, it had been known for a long time, of course, that some blood visited the lungs, but this had always been conveniently dismissed as a thin trickle which was simply used to lubricate or nourish the organ. However, by the end of the 16th century, certain anatomists had begun to argue that the bloodstream through the lungs was much more substantial than that, and that it therefore had to serve a much more important function. So, remembering the fact that blood was dark purple on entering the heart and bright red on leaving it, these anatomists eventually came to the conclusion that the transformation must have taken place in the lungs, and not, as the traditional theory said, in the heart. So, by the end of the 16th century, the stage was set for a completely new understanding of the function of respiration. The end of the 16th century marks the beginning of one of the most fruitful periods in the history of human thought. Less than 100 years after Shakespeare, man's understanding of the physical world had undergone a dramatic transformation. Even the instruments that were made at that time give the impression that a completely new species had taken possession of the world. And yet the men of the 17th century were no cleverer than their Greek predecessors. For them, though, unlike the Greeks, a scientific notion was only to be taken seriously if they could foresee some practical method of proving it wrong by physical experiment. In antiquity, philosophers and scientists tried to solve the secrets of nature by abstract thought alone. They despised manual skill and thought that handiwork was fit only for slaves. But with the rise of Puritanism in the 17th century, there was now a growing respect for craftsmen, artisans, and instrument makers, all of whom were thought to have an essential part to play in the growth of scientific knowledge. This attitude was exemplified by Sir Christopher Wren, whose ambitious architecture was the offspring of refined mathematics and practical stonemasonry. Although Wren is remembered for his great building, he was equally at home in physics and astronomy. In fact, he was one of a group of men who came together in Oxford and in London for the express purpose of asking nature soluble questions, and wherever necessary, putting her to the torture of physical experiment. This remarkable group of men incorporated themselves into a scientific club, and when Charles II granted them a special charter, they called themselves the Royal Society of London. The early members included such men as Robert Boyle, Wren, Pepys, and Isaac Newton. They were all devoted to the experimental pursuit of natural knowledge. And in the early 1660s, they appointed Robert Hooke to be responsible for the collection of apparatus and the public demonstration of important experiments. Hooke had already made his name by recording observations with the newly invented microscope. The illustrations to his micrographia opened vistas upon a completely new world. Hooke, like his other colleagues, was also interested in animal physiology, and especially in the function and purpose of breathing. On October the 24th, 1667, he treated his fellow members to an important and rather interesting display of artificial respiration. Now, what he did was this. Opening the chest wall of a dog, he showed that the animal could be kept alive just as long as fresh air was blown down the windpipe and into the lungs. In this way, Hooke showed that the movements of the chest wall were only important insofar as they served to ventilate the lungs, and that if this job could be done by artificial means, then the lungs could be immobilized without harming the animal at all. Well, the next step was to prove that it was the presence of air in the lungs that was responsible for the blood changing from purple to scarlet. Now, as we've already seen, it was previously thought that the color change took place in the heart. And this view continued to hold sway even when the circulation through the lungs had been widely accepted. So, one of Hooke's colleagues, Richard Lower, showed that as long as the lung was supplied with fresh air using artificial respiration, then the blood ran out of the lung bright red. But as soon as artificial respiration was stopped, then the blood emerged purple and unchanged. Now, in order to prove that the color change was due to exposure to the air, and not merely to its transit through the lungs, Lower poured blood into a long glass vessel and found, just as he expected, that the clot turned bright red on the upper surface where it was exposed to the air and remained dark purple underneath. However, when the clot was turned upside down by emptying it into another vessel, so, then of course the pattern was slowly reversed. On the top surface, what had previously been purple was now bright red, and vice versa. Well, the conclusion was inescapable. The blood had changed color simply as a result of being exposed to the fresh air. And though this exposure, of course, normally takes place in the lung, Lower's experiment had showed that it could happen just as well outside the body in a test tube. So to that extent, it appeared to be a straightforward chemical reaction between the blood and the air. However, it was hard to believe that the blood made its way through the lungs simply in order to enjoy the frivolous luxury of a color change. Presumably, it had undergone a useful change as the result of being exposed to the inspired air. And since Lower had shown that the blood of an asphyxiated animal remained purple, well, it seemed quite reasonable to assume that whatever it was in the air that turned the blood scarlet was the same thing that kept the animal alive. Now, this conclusion begins to make sense of one of the most important signs in clinical medicine. Although it's very hard to show it on film, the appearance of blue lips, breathlessness, and blue extremities, fingers and toes, all add up to the fact that the blood is receiving less oxygen than it needs. When I mention oxygen in this context, I'm really anticipating something which the scientists of the 1660s still had to discover for themselves. Namely, that only a certain proportion of the air is capable of changing the color of blood, and that it's only this proportion, which we call oxygen now, that's capable of supporting life. Until the 17th century, scientists had always assumed that air as a whole was the active principle in respiration. And although they made an important advance when they recognized that this principle acted in the lungs rather than in the heart, the physiology of respiration could make no further progress until it was realized that the active ingredient represented a comparatively small fraction of the inspired air. Now, one man was responsible for making this discovery. He was born in 1643, less than a year after Isaac Newton. He qualified as a lawyer, but spent most of his life studying chemistry and physiology. His name was John Mayo, and by the time he died, at the age of 35, he had discovered oxygen in all but name. In the first of his great papers, Mayo reminded his readers of an important experiment which had been carried out 7 years earlier by the great English physicist Robert Boyle. Now, Boyle had noticed that when air was sucked out of a sealed glass vessel containing a candle, the flame went out almost immediately. But he also noticed that it was possible to exterminate an animal in the same way, which implied that air was necessary both for breathing and for combustion. Well, Mayo carried Boyle's idea on further with an experiment which showed that it was not air as such, but only a certain proportion of it. Mayo placed a candle inside a water seal. Now, his argument was that if the candle was consuming something in the air, the water level would rise as the atmospheric pressure fell inside the vessel. And, sure enough, the water level rose, which implied that the candle was somehow using up the air. And, as you can see, the candle actually goes out long before the water level has risen to fill the vessel. This suggested to Mayo that although there was plenty of air left in the vessel, what remained was useless as far as combustion was concerned. Well, now, the same thing happens, in fact, when a mouse is put inside the water seal. I'm not going to do that. My scruples stop me from extinguishing this scrap of life. But in any case, the experiment doesn't work quite as well as it does with a candle. But nevertheless, as the creature continues to breathe, the water level rises. But just as with the candle, the animal expires long before the water level has risen to fill the vessel. Now, this implies that burning and breathing only make use of a small proportion of atmospheric air. What remains is incapable of supporting either life or flame. Now, the question is this: are the candle and the mouse using the same substance? Or does the air contain two active ingredients, one which is necessary for respiration and the other necessary for combustion? Well, a simple experiment showed quite clearly that they were one and the same thing. Mayo introduced a mouse and a candle into the same sealed vessel and found, just as he expected, that they expired sooner than either would have done if left to die on their own. Well, now this implied that they were both competing for the same ingredient, and that in any given volume of air, this ingredient was only present in relatively small quantities. In fact, about 1/5 of the total volume. Well, now, to all intents and purposes, Mayo had actually anticipated the great French 18th century chemist Lavoisier's discovery of oxygen by more than 100 years. Admittedly, he called it by a different name, but it's quite obvious that he was talking about the same thing. Unfortunately, the significance of his discovery was lost on his contemporaries, and for more than a century, scientists allowed themselves to be misled by a theory which actually prevented them from recognizing the brilliance of Mayo's original insight. Well, it would probably take too long to describe this theory, the so-called phlogiston theory, but it took superhuman efforts on the part of Lavoisier and his collaborators to bring matters back to where Mayo had left them in the previous century. But when Lavoisier came to summarize his findings, it was almost as if Mayo had written the script himself.
We can state in general that respiration is but a slow combustion of carbon and hydrogen, similar in all points to that taking place in a lamp or a burning candle. And that from this point of view, animals which breathe are really combustible bodies which burn and are consumed. In respiration, as in combustion, it is the atmospheric air which supplies the oxygen. But in respiration, it is the substance of the animal itself, the blood, that provides the combustible material.
After the contempt which I heaped on the furnace theory, it seems rather ironic to congratulate Mayo and Lavoisier for identifying respiration with combustion. We seem to be right back where we started from, except that the fire is now located in the tissues rather than in the heart. But it's not quite as simple as that either. When Lavoisier pointed out that animals used oxygen in the same way as the candle did, he wasn't suggesting that the body was on fire. He was merely pointing out that life and flame had certain features in common, that both of them used oxygen and gave off carbon dioxide, and that was as far as he went. We now know that living cells consume their fuel in a very complicated fashion, and although this process involves the consumption of oxygen and the elimination of carbon dioxide, that's to say the same chemical process as burning, what happens in between is quite unlike the burning of a candle, or at least they're only indirectly related. But the fact that they are related can be shown in the following way. If I light a fire in this rather impressive piece of machinery here, energy is released in the form of heat and some light, and of course rather a lot of sound. But unless I harness this energy, it's almost immediately lost. Admittedly, the air becomes warmer and the room is lit to some extent. But to all intents and purposes, the energy is dispersed. But if I use the flame to heat a boiler of water, I can transform the energy released by combustion into a more usable form. I can use it to drive a piston. And if I link this piston to a flywheel, I can make the flame perform mechanical work, just like the muscles. Now, what's more, I can transform this mechanical work into other forms of energy. For instance, I can make the piston cause a coil of wire to revolve inside a magnet. And as a result of doing this, I can generate an electric current. And if I lead this off through a torch bulb, I can get right back to where I started and recreate heat and light. Admittedly, the heat and light put out by the bulb here is considerably less than what was put out by the gas fire at this end. This implies that I've lost energy somewhere along the line. Some of it's been wasted, of course, by loss from the unlagged boiler, and then we've had to overcome the friction of the moving parts, and we've had to heat them up as well, and the electric wire has also got warmer, and so forth. But if I could measure all these unprofitable losses and add them to the work done by the torch bulb at the end, we'd find that the total energy of the system was the same. In fact, by the middle of the 19th century, by which time engines like this had become commonplace, it was apparent that energy was neither created nor destroyed, but merely transformed into various types of work, some of which are more immediately useful than others. Well, it's just the same with living cells. This crackling electric pulse is being made by a single nerve cell. It's possible to record it by poking a small electrode right into the living cell itself. With the aid of oxygen, the cell unlocks the energy which is bound up in the molecules of food and transforms it into electrical work. And the same source of energy can be transformed into rhythmic mechanical work. On the surface of the windpipe, microscopic mobile hairs form an escalator which cleans it and frees it from foreign bodies. But even this mechanical work needs fuel and oxygen. Cell divisions like this may not look very strenuous, but the work of growth and development would soon come to a standstill in the absence of oxygen. When organisms are as small as these cells are, they can absorb all the oxygen they need through their naked surface. But when an animal is as large as this one, and when its surface is impermeable, it has to have a special organ for absorbing the oxygen. It also has to have red blood for transporting the gas and an active circulation for distributing it to the working tissues. Now you can think of the lung as a vast inland harbour, except of course it's filled with air rather than with water. Now the air is drawn in through a series of branching tubes which divide and divide, getting smaller and smaller as they go, until they finally end up in millions and millions of very thin-walled sacs called the alveoli. Now you can think of the alveoli as wharves or quaysides. Now the bloodstream forms the road transport system, which travels through the lung, visiting each of these key sides. And here, a very vigorous import-export business takes place. Oxygen is taken out of the air and loaded onto the container transports, those are the red blood corpuscles in the bloodstream, and at the same time, the carbon dioxide, the waste stuff from the tissues, is offloaded from the bloodstream and into the lung and blown off into the outside air. Now, the only drawback of an arrangement of this sort is that unless the chest is kept ventilated, the air inside this great inland harbour becomes stagnant and unusable. And that's exactly what happens when patients have their chest movements paralyzed, say in poliomyelitis, or if their neck is broken. And unless the patient is artificially ventilated using a respirator, they run the risk of asphyxiating themselves. But how are the normal movements of respiration carried out? Well, the human lungs are quite unable to move on their own. But because they're enclosed in a bony container whose volume can be changed in several different directions, the lungs can be filled and emptied. The ribs are slung from the backbone like hoops of a barrel, and by muscular effort these hoops can be raised, which increases the diameter of the chest. The floor of this container is formed by a muscular piston or diaphragm, and when this is lowered, the depth of the container is increased. With each of these movements, the lungs expand and air is drawn in through the pressure of the outside atmosphere. By physically squeezing and expanding the lungs, the inland harbour is rhythmically replenished. This tidal flow is normally about half a litre. In fact, the amount of air in the chest is much larger than that, and you can blow out a vast reserve. In someone of my size, for instance, it's about 6 litres. So that the air isn't entirely renewed with each breath. Now, that doesn't matter as long as the process repeats itself from moment to moment, as long as the turnover is enough to meet the oxygen uptake of the blood which is circulating through the lung. But if the patient becomes too fat, it's almost as if he was wearing a lead waistcoat, so that the size of each breath now becomes smaller as a result, so that the turnover is insufficient. Now, in order to prevent the air from becoming stagnant, it becomes necessary to increase the rate of respiration, which is one of the reasons why very fat people often seem to be breathing faster than usual. Of course, the other reason is that they're also carrying around more weight, which means that their oxygen needs have increased as well. But if the fatness is severe enough, the breathing becomes so shallow that the increase in the respiration rate isn't able to keep up with the need. The atmosphere in the lung becomes dangerously low in oxygen, and at the same time heavily contaminated with carbon dioxide. The patient becomes drowsy and even confused. Now, it has been suggested that the sleepiness of the fat boy in Pickwick Papers was actually due to this. Nowadays, the respiratory symptoms of the very fat are sometimes referred to as the Pickwickian syndrome.
Now, if you put your chest against this, please, sir, and chin on the top.
Fat is not the only thing which can interfere with the movements of the chest. They can be obstructed by changes which are not apparent to the naked eye and which need much more subtle techniques. Fluid, for example, can unobtrusively fill up the space between the lung and the chest wall in an illness like pneumonia. It's easy to show this on an X-ray because the fluid casts a white shadow over the darkness of the air-filled lungs. Of course, you can also get air in the pleural space as well. That's what we call pneumothorax. You can see that quite clearly on this X-ray here. All that's left of this lung is the pale triangular shadow right on the edge of the heart's silhouette. Now, since the patient is now working with one lung, he's naturally breathless. But of course, you can also get water and air in the pleural cavity. That's called hydropneumothorax, and in that case you can actually see a hard line, which is the upper level of the fluid. But of course, in the case of fluid fat and air, all the restrictions lie outside the lung, as if it was surrounded by a rigid casing. But you can get just the same effect if the consistency of the lung itself is altered by disease. If the tissues become extensively scarred by breathing all sorts of industrial irritants, like coal dust, for example, as you can see on this X-ray of someone who's been down the mine a long time, then you can get scars, which are these blotchy areas here over the lung. And when that happens, the lung loses its natural elasticity, and in order to make up for the small size of each breath, these patients have to breathe more rapidly than usual. Now, this loss of elasticity is one of the reasons why patients suffering from heart trouble are also found to be breathless. You see, as the muscular pump fails, the circulation through the lung becomes sluggish, and the lung itself becomes rigid with engorged blood, so that the amount of air that can be drawn into the lung at each breath falls. So the patient simply has to breathe faster than he would otherwise. In all these cases, though, the breathing changes quite automatically. That's to say, it's a reaction rather than a voluntary act. In fact, as far as the patient himself is concerned, the rapid breathing is an uncomfortable inconvenience. He's quite unaware of the fact that by taking more breaths each minute, it's the only way he can overcome the inadequacy of each individual one. So how is the change brought about? Well, let's think of it like this. We've already agreed that the ultimate purpose of breathing is to keep the cells of the body adequately supplied with oxygen, at the same time to keep them free of their own carbon dioxide. So one could imagine a mechanism, a sort of automatic alarm system, which was activated whenever certain special cells experienced a dangerous fall in blood oxygen or an equally dangerous rise in carbon dioxide. And then, whatever the cause was, this alarm system would automatically set off the appropriate increase in ventilation. Well now, it so happens that the nerve cells of the respiratory center are so sensitive to these gases that they perform this alarm function for themselves. In fact, whenever the blood alters its composition, whether from the effects of obesity, heart failure, pneumonia, anemia, or whatever, the activity of the cells in the brain makes sure that the ventilation is automatically adjusted. Now, you can prove this quite easily by altering the composition of atmospheric air in an otherwise normal subject. Now, for instance, if I rebreathe my own air, that's to say by blowing in and out of this sealed container here, then the atmosphere I breathe will gradually begin to lose oxygen and start to accumulate carbon dioxide. And presumably, by the same token, my blood will start to change in the same way. So if you watch this pen moving up and down the chart here, you will see the ventilation begin to change quite dramatically. In this arrangement, my lungs plus the mobile reservoir enclose a single sealed volume of air which moves backwards and forwards from one compartment to the next. I'm rebreathing the same air over and over again, taking oxygen from it and adding more and more carbon dioxide. My blood changes in the same way, and as it circulates through the sensitive cells of my brainstem, a signal is sent out to try and overcome the crisis by taking deeper and deeper breaths, which you can see on the pen recorder as the waves increase in size. But since the system is closed, that only makes the problem worse. My only escape from this vicious circle is to come off the apparatus altogether. So whenever the cells of the body experience a critical change in their oxygen supply, the breathing is always intensified in the attempt to overcome the situation. Now, the signal, in fact, is given much more by the build-up of carbon dioxide rather than the fall of oxygen. But the effect is the same, since the two, of course, are linked. The patient takes larger and more frequent breaths to try and compensate. Now, if the carbon dioxide alarm signal is filtered out, then disastrous consequences can follow. For instance, if I was to breathe into this spirograph through a potash filter, which I'll now fit on, the carbon dioxide in the air is now filtered out before I can breathe it. Now, this would have the effect of removing my most important warning signal. Right, having fitted the potash filter, if I now continue to breathe my own air, each time, of course, I'll take in less and less oxygen. My cells will be deprived, and I'll soon cease to function normally. I'll lose my faculties one by one, perhaps even faint. But the difference is, at this time, I won't be immediately aware of the lack of oxygen. In fact, my breathing rate should remain more or less the same. And this is what happens to high-altitude flyers if they lose their oxygen supply. You see, their carbon dioxide is being blown off into the atmosphere, so it's not there to act as a stimulus, but the oxygen is falling nevertheless. However, they're quite unaware of the fall of oxygen, and they start to behave in a peculiar fashion without knowing what they're doing. And they might even attempt to make three-point landings on clouds. So, I fitted the potash filter, and I'm going to breathe in and out of this sealed chamber and see what happens. I hope to see you in the next program. Incidentally, I'm also going to write down a list of the alphabet, and you'll gradually see me becoming more and more aberrant as time goes on. In this experiment, I was careful to ignore the movements of the pen on the machine for fear of influencing my own breathing. It was only afterwards, when I examined the tracing, that I noticed this slight increase right at the start. That early on, there couldn't have been any change in the air, so I can only assume that it was due to anxiety. In any case, it settled down once I became absorbed in the task of repeating the alphabet. And that's the interesting thing about breathing. It can be performed consciously, unlike the heartbeat. But there's no risk of it stopping if your mind happens to be on other things. The brain broadcasts a regular pulse to the muscles of the chest. And although you can change the rhythm at will, to speak, sing, or whistle, it soon reverts to a quiet rhythm once it's left to itself. This rhythm can change automatically, just as it does with the athlete, if there's a need for more air, as long as the need is recognized and signaled. In this case, though, it had been carefully eliminated. So, although I was using up oxygen with each breath, my brain was unaware of the fact, and my breathing remained more or less steady. What's more, I was unaware of what was happening. Towards the end, I had no idea that I was making such a mess of the alphabet, or that I was gliding into unconsciousness. easy it is for a simple man-made device to make a fool of the wisdom of the body.
Okay. 102, take one handboard.
Give us a second mark. Okay.
102, take one handboard.
Second crack.